This is going to be our first lesson, setting up Riemann integration for scalar-valued functions of multiple variables. So ultimately, we are interested in discussing integrability where the functions, say f, that we will look at are going to be scalar-valued, but their domains will be subsets of n-dimensional space Rn. Before we do that, though, I want to take an entire lesson just to revisit the key ideas from analysis 1 when we look at Riemann integrability for functions of one variable. So this video will not go into higher dimensional domains at all. I expect that you've seen all of this before, but if you haven't, technically this is a standalone lesson that will prepare you for the next lesson when we set up all of the same ideas. So analogous ideas to, say, this first idea of a partition for functions of multiple variables. Okay, so this is a review, and it's also to make sure that we are all on the same page, that we have the same kinds of notation and vocabulary that we're going to need to start talking about Riemann integrability for functions from Rn to R. Okay, the very first thing that we should define together is the idea of a partition for a domain. If we are talking about functions of one variable, and we're looking at, say, doing an integral of such a function, typically we integrate from a to b. So let's say this is the real number line. It's the domain for some function f, which for the purposes of today will be a function on the domain from a to b to r. And this domain is what we are going to generalize and broaden in future videos. Okay, so let me graph this, or at least put it on this picture. So say I have this closed bounded interval from a to b. A partition of this domain is any way to cut up the domain. In words, that's what it is. But basically, it's a collection of points, starting with a and ending with b, that subdivides this interval. So here's like my first cut is right at a. Subdivides this interval up into little subintervals. Okay, so typically to describe this particular partition, what I would say is the partition P. It's a set of points, and each point in the set is like the slice position. So the first one is A. And to make that fit into the way I denote the rest of the points, I would call that x sub 0. And then my next slice point is happening here in the picture, so that would be x1. And then this one's x2. All the way through x sub capital N, which is also what we would call B. Okay. So in this ordered collection of points, we have a total of capital N plus 1 because this first one is got a subscript of 0. So overall there's N plus 1 here. Sorry, I just realized I switched from little n to capital N. So let me do that. It would be a little bit dangerous if we were working with dimensions in, if we were working with domains in Rn, but we're not going to do that in this lesson. So I will stick with lowercase n. This collection of n plus 1 points slices up our domain from a to b into n subintervals. This subinterval, well, in the picture, I can tell you that it goes from x3 to x4. I just add that here. This was x0, 1, 2, 3, 4. But notice it is the fourth subinterval. Here's the first one, second one, third one, fourth one. So in general, the ith subinterval goes from xi minus 1 through xi. Like that. So I always remember it as we index with the right endpoint when we are slicing up, say, this domain from a to b. Typically, if you were actually going to do a computation with a partition, which you might do in calculus when you set up something like a Riemann sum, usually you slice up your domains into evenly spaced subintervals. I deliberately drew this picture, though, so that they were not evenly spaced because that's not at all required. So in the definition of Riemann integration, we allow for your partition to chop up the interval from a to b any way you want it to. So in particular, I made this one fairly large, partly because I knew I was going to label it, and partly just to emphasize that, it's okay that this subinterval is really wide and this one's really narrow, and I don't necessarily have a prescriptive form for how wide each of these subintervals is. I don't have a prescriptive form, like I'm not going to give you a formula for it, but I will tell you that the width, I think this marker is not very good. I apologize. Let me rewrite this. The width of the ith subinterval is delta xi. In a partition where everything is evenly spaced, that could be a fixed number, would be a fixed number. Here, it's quite possible that every single one of these widths is different. So this is something that would vary as I varies from the start to the end of our partition. And of course, in this particular case, the width is going to agree with our geometric understanding of what width should be. It's going to be right point minus left point. So there's a way to compute that for the ith subinterval. Okay, this is just looking at the domain of integration, but now we're going to talk about the function. We're going to switch to a new set of notes in just a second. Before I do that, though, because I'm going to erase this picture, you want to imagine that you have a bounded function over this interval from a to b. It's bounded, it's not necessarily continuous. I will give you some graphics where I've deliberately set up a function which is not continuous. So often when we draw a function, we draw something continuous, right? So train yourself when you're sketching notions with integration not to always draw continuous functions, but they should be bounded. We're not talking about improper integrals that have asymptotes and things like that. Oh, this is continuous. I was trying to draw something not continuous here. There we go. Okay, so it should be a bounded function that we're imagining over the entire domain from a to b. Since it's bounded from a to b, it is bounded over each subinterval. Therefore, if I think about a bounded function over each subinterval, it makes sense to identify its supremum and infimum for the function outputs. It could be that the function attains its supremum and infimum. We could be looking at, say, having a function maximum and a function minimum over each of these subintervals, but it's not required. So here it looks to me like over this subinterval, this function has an infimum value that is not actually the minimum, but it has an infimum. So a bounded function over each subinterval here will have a supremum and infimum, and those values will go into our next set of definitions. Picking up with the discussion that we were just having, if we are looking at a function f, which is bounded over the entire domain from a to b, it is bounded over each subinterval. So then what we can do is say, well, to each subinterval, like this ith subinterval from xi minus 1 through xi, associate a number, which is the supremum of the set of outputs that f takes over that subinterval. So the first subinterval gets capital M sub 1, the second interval capital M sub 2, all the way through the last subinterval will be capital M sub n. So it's a collection of n values associated with each subinterval. We will use that now to construct something called the upper sum of f with respect to the partition P. I use the notation capital U of f comma P. You might see something like U of sub P of f. I've seen that one, as well as maybe some fancier looking notation, but hopefully it's clear to you what it's talking about. So the upper sum of f with respect to P is a sum. It's always a finite sum because a partition is always a finite collection of points. So once you've made a partition, you have n points where that's a finite number. So this sum, it's a finite sum. It will exist. And what we can say is we're going to add up all of these products where we're going to take each supremum value and multiply it by its respective subinterval width. The supremums are something you want to compare to function output. So you think of that as a height. And then delta xi is a width. So these products here are all quantities which geometrically we can think of as a height times a width. Therefore, what we are saying is for each subinterval, create a rectangle with this height and this width, multiply that together to get that rectangular area. You will have n such rectangles, add them up. So this is a sum of rectangular areas. And I'm going to write sum of tall rectangles because we used the supremum values. So if I say, oh, it's the tall rectangles, you'll know what I'm talking about. It's the picture that you generate when you set up your partition and then you pick the sups for the function. Okay, the thing is, this depended on how we partitioned the domain from A to B. If I partition it differently, we might have different soups. If our function's changing a lot, we're going to have different soups over different ways to slice up the domain. We'll have different widths. And, how many ways can you partition the domain? Well, uncountably many. So, if you just randomly start chopping up a domain, there are uncountably many possible partitions that you can create. However, I claim that if you look at every possible partition, all uncountably many of them, it makes sense to say that the set of all possible upper sums of f with respect to any possible partition, that set is bounded below and therefore has an infimum. Okay, so that is that mentally imagining every possible partition. I'm trying to lead you to the third definition here, which is what we call the upper integral of f over the domain from A to B. And what it is an infimum of every single possible upper sum that you could ever find, or even beyond. Okay, take a moment here to pause and see if you can perhaps prove or reason out why this infimum must actually exist. So I claimed that the set of all possible upper sums is bounded below. How do I know that? Can you come up with some concrete explanation for why this set infimum exists? After I stepped away, I was thinking about this product here, height times width, and I said it's an area. So what you're adding up here is in rectangular areas. And that's basically right, but it's quite possible that your function is negative and the supremum is also negative, in which case it would be still an area, but it would pick up a factor of -1. So in case you were wondering that or you wanted to ask it, let me throw the word signed up here just to indicate that, this product, geometrically, it does represent an area, but if your supremum is below the x-axis, it's going to be a negative area. So -1 times the area. Okay, so just a little aside. For the question that I just posed, if we could somehow imagine all possible partitions of the domain, which we can't really because there are uncountably many, for each partition, there is an upper sum of f with respect to that partition. So we could think about the set of all possible upper sums. That's a set of numbers, and I claimed it was bounded below and therefore has an infimum. This is supposed to be a review video, so I don't want to go off track into writing out a formal proof, but let me just sketch the argument. F is bounded, so I can say it has some global lower bound. This could just be any number that serves as a lower bound, and some global upper bound. So across the entire domain from A to B, F sits between little m and capital M, which means that all of the sup values also sit between little m and capital M. Again, I'm just sketching out the argument here. So if I were to look at, say, the ith supremum, it's also between this global lower bound and global upper bound. So therefore, this is true. And I need a new marker. So now, if this is the summand for each upper sum. If I now add this up from I equals 1 through n, we can say the sum from I equals 1 through n of this constant value m times delta xi is less than or equal to, let me just say here, no, I'll go ahead and write the sum. I was going to replace it with upper sum, but I'll do that in just a second. And then on the right-hand side, we have also the sum from I equals 1 through n of a global upper bound times delta xi. If I take this number, little m here, it's a constant, I can pull it in front of the sum. And then I'm saying add up all of the widths of all of the subintervals. Well, that's going to give me the length of the original domain. So this is little m times b minus a. This is the upper sum of f with respect to whatever partition I'm considering. And this is capital M times b minus a. There's no partition specified here. This is true for every possible partition of the domain. Therefore, every possible upper sum sits between this number and this number. So in particular, it's bounded below. And therefore, there is indeed an infimum for this set of all possible upper sums. When we turn it around in just a second and look at lower sums, we will have a similar conclusion. It will be a bit flipped, and it's the exact same type of argument. So we will skip the justification in that case. Since this set of upper sums of f with all respect to all partitions is a set which is bounded below, it has an infimum. That infimum is a number, and that is what we will call the upper integral of f. At this point, it's independent of specifying a partition. It is just the upper integral of f over the domain from A to B. This computation that we just did is true for any bounded function. You might be wondering if I'm requiring some integrability here. We haven't defined integrability yet. Any bounded function has a sup over each subinterval. Therefore, you can do this computation. Therefore, you can take the infimum. So this is always, these three constructions are always possible for every bounded function over the domain. What I would like to do now is step aside just for a second. I want to put up some pictures of upper sums of f with respect to different partitions. So I just have this little computer graphic that I created to try to illustrate what this would look like for, say, a function which is not continuous on the domain from 0 to 4. Then we will come back and we will talk about lower sums, lower integrals, and that will lead us to our definition of integrability. This is a demonstration I wrote in MATLAB where we are going to take this function, which is bounded from 0 to 4, although it's not continuous, that's fine. And what I'm going to do is just illustrate a few different upper sums of f with respect to different partitions. Let's start with a partition that generates 3 subintervals, therefore it has 4 points. And, I'll do a few different ways to partition this domain into 3 subintervals. And, MATLAB is randomly designing these subintervals, so they're completely random looking. I just want you to recognize that the upper sum of f with respect to each of these partitions is a sum of 3 rectangular areas. That's all it is. Let's do 10 subintervals now. So we'll look at a few different versions of 10 subintervals, again, randomly designed by MATLAB. And now we have 10 rectangular areas. You could do more. I think the program gets a little slow if I go up to like 20, 30, but the idea is for each possible partition, now we've seen several different partitions of this domain. The upper sum that we would then compute with respect to any of the partitions that we choose is just a sum of a bunch of tall rectangular areas. So I just think of them as tall rectangles. We haven't talked about what the Riemann integral of f could be geometrically, but if you're anticipating a discussion of area under the curve, then I like to think of these tall rectangles as overestimates to that number. So for me, tall rectangles, they're tall, they overestimate a quantity, which here we might think of as area under the curve. Just changing our point of view to look at infima instead of suprema, let's quickly run through these 3 definitions. They are analogous to what we've already discussed. If you have some partition P over each subinterval, f is bounded, so it has an infimum. That's what we call little m sub I. That is, again, something you want to think of as a height. It's probably lower than the supremum over the same subinterval, but it's still a height. So on the second line, when we create the lower sum of f with respect to our partition, it is once again the sum of a bunch of signed rectangular areas. It's just, I think of these as the short rectangles. So here we have tall rectangles, here we have short rectangles. I will often call this the overestimate, I'll call this the underestimate. Anyway, it's the exact same notion, just the heights are lower. The proof that we did, or the proof sketch rather, that we did, where we proved that every possible upper sum of f with respect to any partition sits between the numbers little m rather times b minus a and capital M times b minus a. The exact same proof you could reproduce, maybe just slightly changing a few things to show that all lower sums are also bounded in the same way, and therefore the set of all possible lower sums is bounded above. Therefore, it has a supremum value, and that value is what we call the lower integral of f from a to b. Once again, these 3 computations exist for any bounded function over the domain from a to b. The question is, we're trying to get to integrability. What might you anticipate will be the connection between the upper integral and the lower integral? Before we establish that, let's go back to our visualization. I will just put up a few lower sums just to make sure you're picturing the right thing. Same context as a moment ago, same function over the domain from 0 to 4. Here are some sample lower sums of f with respect to different partitions. Again, I just want you to picture this so that when you see that computation, you know what to mentally imagine. Here we have short rectangles. So before we had tall rectangles, now we have short rectangles. You can think of this as underestimating rectangles. So they sit over, for each subinterval, they sit under the function. Let me now put together upper sums and lower sums. So this graphic will have both, which means that if I wanted to analyze the difference between the upper sum and the lower sum, what I'm really looking at is just kind of the gap that you see at the very top. So from the top side of the each lower rectangle to the top side of the upper rectangle, it's just a little gap. I mean, it could be, for a given partition, it could be a sizable gap, but that's the difference between the overestimates that we associate with upper sums and lower estimates that we associate with lower sums. Now, let me put up a few different partitions here where we are chopping this domain fairly finely into several subintervals. And what you'll notice, because I actually have the computations here, is that the gap between the upper sum and the lower sum in general, it's shrinking. The idea with integrability is, can we perhaps partition well enough? If I really chop this domain up finely, can we partition well enough so that upper sums, they go down as much as they can, lower sums go up as much as they can, and essentially, can we make them meet somewhere, like meet roughly in the middle of where they currently are? If we can, that is the idea behind integrability. So when you think about partitioning a domain, you want to imagine that the more you chop it, if you get finer and finer, in general, what will happen is your upper sums will come down, your lower sums will go up, and if you can make them meet somehow, or you can imagine that they would meet if you could consider every possible partition, then that tells you your function is Riemann integrable. So let's formalize that before we wrap up this lesson. Based on the visualizations that we were just looking at, I think these four statements will not be surprising. They are fun proofs. I think each one is just a couple lines to prove. I'm going to try really hard not to let myself prove them in the interest of time. Imagine that we have a bounded function from A to B, and P and Q are just any two possible partitions of that domain. The lower sum of f with respect to, say, the partition P is less than or equal to the upper sum of f with respect to the partition P. So lower sum with respect to a partition is always smaller than the upper sum. That shouldn't surprise you. Imps are always less than or equal to sups. I'm going to try not to prove, so let me stop there. If I take a partition P, or if you think back to how we wrote down a partition, it was a set of points. If I drop in a few more points, which you could imagine as taking P and then adding in some extra slices to maybe take subintervals and split them up, that is called a refinement. And what happens when you refine a partition is your lower sums go up, your upper sums come down. So if you read this carefully, you'll see that the lower sum of f with respect to the original partition is less than or equal to the lower sum with respect to the refined partition. But also, the upper sum of f with respect to the original partition is greater than or equal to the upper sum with respect to the refined partition. So it's like the more you slice, you raise up lower sums, you lower down upper sums. So it's like you're kind of pushing those numbers a little bit closer together as you refine and refine. The third line item says, given any two partitions, which may or may not have points in common, the lower sum with respect to, say, P is less than or equal to the upper sum with respect to the other one, Q. So all possible lower sums are less than or equal to all possible upper sums. There's no clever way to slice so that a lower sum jumps over an upper sum. I don't want to write any proofs down, but to do this, what you would do is take P and Q and create their common refinement. So you can imagine the sets of points that define both of those partitions, just group them together into one set. You've refined both of them, then you use this one. Okay. Since lower sums are always less than or equal to upper sums, when you then take the supremum of all of the lower sums and the infimum of all of the upper sums to get the lower integral and the upper integral, you have this inequality. To wrap up, before we move into Riemann integrability, just want to really emphasize that for any bounded function from A to B, its lower integral exists, this number exists, and it is less than or equal to this number. The question is, are they ever equal? The answer is yes. And if you don't believe me, just consider a constant function. You can think about that. But a constant function is not the only example of a function for which over some domain from A to B, the lower integral equals the upper integral. In fact, that is the definition of a Riemann integrable function, and the shared value is what we would call, in more traditional notation, the integral of f from A to B. So that is going to be our definition of Riemann integrability. We can imagine the more and more we refine partitions, our upper sums come down, our lower sums come up, and they get closer and closer together. Here's the catch. The definition of lower integral and upper integral, these are defined over all possible partitions. And as I said, they're uncountably many, so you can't check every possible partition. And also, it's going to turn out that you can't always get an upper sum which is actually equal to a lower sum. Just consider a basic monotone increasing function. Say this is the graph of f over A to B. Oh, A over here, B over here, like that. No matter how you partition this domain, it will turn out that your upper sum is strictly greater than your lower sum, because over every subinterval you could make, the sup is going to be strictly greater than the inf. You're never going to have a clever partition of this domain which causes those two numbers to actually coincide. But as you partition this more and more, the upper sums will come down, the lower sums will come up, and they will get arbitrarily close together as you create better and better partitions. That recognition of what's happening with this function is exactly what we see here with Riemann's condition for integrability. Since we cannot consider every possible partition, and in some cases, even if we could, we won't get, equality in any particular sums that we create. This is a really nice way instead to show that a function is Riemann integrable. I'm not going to do the proof here. It's actually pretty quick to prove it. You're really just saying that you can make that inf of upper sums really close to the sup of lower sums, arbitrarily close. In fact, okay, I'm getting dangerously close to writing a proof down, so let me just state this. Riemann's condition says that a function f on what I should call the interval from A to B is integrable if and only if for any choice of positive number epsilon, once you've picked that choice of epsilon, you could then go make a single partition, which every time we use this, we will denote that partition p sub epsilon, so that the gap between the overestimate with respect to that partition and the lower estimate with respect to that partition is less than epsilon. So it's like you're forcing the upper sum and the lower sum to be really, really close together. Since epsilon here is arbitrary, that's going to lead you to this equality. Okay, I think we'll wrap up there. All of these notions we will carry forward in the next lecture to consider functions where the domain is a subset of Rn instead of just the number line R. Thank you for your attention.